So this slide shows the second one. It just talks about simple harmonic motion. Hopefully you've learned about what it is and how it works, and you can identify some things about it. This part just deals with figuring out things about them based on the position time graphs of that simple harmonic motion. Now, the motion of the object would make a great position time graph. We can look at those and see. There's the first picture. It's at point A, so I'll make a dot for it on our graph. Second picture is at x equals 0. It's a little further in time, so I'll make a dot for that. The third picture is at x equals -a. It's on the left-hand side. That's going to be below the time axis, so I'll put a dot for that. Now, when it goes back from left to right, I'm going to get dots for that as well. It's going to go back to equilibrium, then all the way over to the right, then back to equilibrium, then all the way over to the left, then back to equilibrium. Well, you get the idea. And if I sketch that out, it's not going to look like a zigzag pattern. It's actually going to look more like a curved line. Okay. It's going to look like a sine wave. I apologize because my line is kind of wavy there. But it's going to look like a sine curve. We're not going to worry about making a sine curve, but we are going to worry about using that shape of the line to describe what happens. Now, if we read that graph, we can actually figure out all those quantities that we were measuring earlier. Okay. So the first thing we're going to do is we're going to measure the amplitude. The amplitude is the distance from equilibrium to the maximum point. Well, we can see that the equilibrium is this line down here. So it's at 0. Okay. And the maximum point is up here at 2. So if I subtract those 2 minus 0, I'm going to get an amplitude of 2 centimeters. The next thing I want to do is I want to find out what the period is. Well, I'm given the time in centimeters, or sorry, time in seconds. So I can just find the time when it gets, and you can see that we have the time when that's at the maximum point. Then it gets to the other point. Then it gets all the way over to here. Okay. Well, at this time, it's time equals 0. This time over here is time equals 3. Well, if you subtract those two, you get a time of 3 seconds. Okay. And we could have picked other points and gotten the exact same result. And again, to find the frequency, we just take the inverse. So it'd be 1 over 3 or 0.33 hertz. Okay. So you can do it with any graph that you want. We're going to try it again with a different kind of graph. This next one is different. Okay, that's a little longer, but I'm not real concerned about that. What I am concerned about is that this time our equilibrium point is in 0. It's kind of a pain. Okay, if you look at it real closely, you can see that it's the point in the middle. I'm going to draw that. It's like right here. Okay. And if you track that, you get an equilibrium point of 0.23 because it's just below that part there. If I measure the distance, this is at 0.28. So from 0.28 to 0.25 or 0.23 gives me 0.05 meters. Okay. I can take my period from anywhere I like, but this time I don't have the comfort of starting like at 0 very well. So I'm just going to pick points that are easy for me. I think this one is at like 2.1. And I looked for a point over here. It looks like it's about at 2.9 almost. So it's at about 2.2. I'm sorry. So this is close to 2.2. And this one here is close to 2.9. So when I subtract them, I got 0.7 seconds. Okay. And then when I take the inverse of that, I get 1 divided by 0.7. It's about 1.4 hertz. I rounded a little there. So I was able to get those values that way.